Okay, let's see if we can go through these ones a little bit quicker so it doesn't take one video per example. Here we have solid copper reacting with silver nitrate solution. Copper is elemental and we're told it's solid. Silver and nitrate are both single positive and negative charges, so they go together in a 1-to-1 ratio. I recognize this as a single replacement reaction, and as I do more investigation here, I see that I have two metals, but only one anion, so it is the two metals that do have to switch places. So that means silver gets kicked out on its own, and so silver should just be elemental and therefore solid. Our elements are as they are, just like they would be on the periodic table. And that leaves us with copper nitrate. Now for this one, we should take a closer look at copper, and you can see that copper has two charges. The question doesn't tell us which one, so which one should we likely go for? Well, remember, the most common charge is listed first or on top, and so most of the copper I would have in this sample would form copper 2+ ions rather than copper 1+. So, with copper 2 and nitrate, and this should produce Cu bracket NO3 bracket 2, and now I just need to see, will this dissolve? Something that we're going to learn pretty quickly here is that nitrate right there, most things with nitrate are soluble, and then we look down here, you'll see no nitrates anywhere in this category, so we can assume for Chem 20 that all things with nitrate are soluble. So, I can go and realize that this one will be aqueous. I still have some balancing to do, so I should get that out of the way. And so 2 nitrates is probably my best place to start. It's the highest number I have in the whole chemical reaction. And so 2 nitrates there requires that I balance with a 2 over here for silver nitrate to fix those, but that changes my silvers. So I double up my silver. I have one last thing to look at. I haven't looked at copper yet, and you can see it's 1 part copper on either side, so it's already balanced. Now I just need to go through and come up with my total ionic. Well, copper is not a strong acid or an ionic compound that dissolves, so it is just left as is. Silver nitrate, because it's aqueous, is a soluble or dissolvable ionic compound, therefore it must dissociate. Remember the 2, and so I have 2 parts silver ion, and I have 2 parts nitrate ion when that dissociates. Silvers, again, as a metal, we would see this as a black precipitate in the reaction, but it's not one of our 2 things that produces new ions in solution, and so I just write it as is, and we found out that copper 2 nitrate is also a soluble ionic compound, so it will break apart into 1 part copper 2+ ion and 2 nitrate ions. And now what I want to do is go through and look for things that have not changed. If I look at copper, it changed in both state and charge, so it must be involved in the chemical reaction. Silver changed in both state and charge, but nitrate has undergone no change whatsoever. So only one spectator ion in this one. All right, the ones that we cross out are called spectator ions, and so the remaining reaction just happened to be between the solid copper I added to the beaker and the silver ions that were dancing around in the beaker's solution. And they've caused a switch and a change in places. And we can just double check that things are still balanced, but there is my net ionic equation. So these are generally done in 3 parts. As you get better with them, you will be able to take the odd shortcut, but I would encourage you to do this. All right, here is your non-ionic, here is your total ionic, and here is the net ionic with the spectators canceled out. Okay, here's another one. We have sodium iodide solution reacting with chlorine dissolved in water. That's still elemental. And so if we take a look at what we're going to get here, I see a single replacement reaction again, and I see 2 nonmetals are the ones that will switch places. So iodine is going to get kicked out, and our halogens do dissolve, but if you were to write I2 solid, I would be just fine with that one. Our data table doesn't really give us enough information, but I know that I have iodine and chlorine in my halogens are soluble. All right, that means chlorine comes over here to bond with sodium, and so we know that sodium chloride is an NaCl, and I know from experience that NaCl is soluble, but of course you can check it on the table. If we take a look at Cl, most things are soluble, and you will not find Na down here. So your chart defends that. I just sped up the process because I know table salt dissolves. Okay, so now we have to take a look at what will either be a strong acid or what will be a soluble ionic compound. And so for that, NaI is a soluble ionic compound. So after I do my quick balancing here that I keep wanting to forget, all right, I would have 2 parts sodium, and I would have 2 parts iodide. Chlorine would not change. Remember, it's only the ionic soluble compounds that we cause changes in, or write down those dissociative changes. Therefore, my I2 would stay the same. But here's another soluble ionic compound, and so I would end up with 2 parts sodium ion and 2 parts chloride ion. So this all comes down to recognizing those 2 things, soluble ionic compounds and strong acids. So far we haven't seen any strong acids, but we've seen lots of soluble ionic compounds. If it doesn't fall into one of those 2 categories, there is no change made between this non-ionic and the total ionic. Okay, that's why chlorine and iodine did not change. They were not one of those 2 things. We now take a look at it. I see sodium ions over here. Oh, I see sodium ions over here, so that means sodium ions did not participate. And away they go. I have iodide ions here, but I have iodine. All right, so I see a definite change. The charge and the proportion is written differently. Chlorine and chloride, the charges are different, and how they're written as molecule versus 2 ions is different. So they remain as parts of the players in this chemical reaction that did participate. So sodium was just the spectator ion. It didn't change throughout the reaction, and therefore we can ignore it in the overall equation. So this equation generally bumps down to, or boils down to, 2 iodides reacting with chlorine in solution to produce iodine and 2 chlorides in solution. There you go. All right, one more. We'll try and sneak this one in here. So this is the last video for chapter 7.1, and you can see we have a couple of things here. Again, this looks like double replacement. Okay, I see a strong acid of hydrochloric acid. Remember our cheat. Even though acids are molecules, if you pretend everything about them is ionic, then it does work out for predicting new products and things like that. Naming and so on and so forth. So if I have HCl and I have an ionic compound of NaOH, then it's the hydrogen and the sodium that should switch spots. Hydrogen comes over here to bond with hydroxide, and so we get water. I've just written it as HOH for easier balancing, and so that will be a liquid. And I have sodium coming over here with chloride, and so there's that NaCl again, and I know that table salt does dissolve in water. When I look at my balancing here, everything is in a 1-to-1 to 1-to-1 ratio, so it is already balanced. Now I can start breaking up my strong acids and soluble ionic compounds. So HCl is one of my strong acids. Okay, remember that they produce brand new ions in solution. The hydronium ion, which is easier for us right now to write as H+, and the associated anion of chloride. NaOH, that's a soluble ionic compound, so I get sodium ions and hydroxide ions. Water is a liquid, so it just stays as, if you like, H2O. HOH or H2O, both work, they're just fine. And then NaCl is this soluble ionic compound, and so I have Na plus ions, and I have chloride ions. So taking a look at what did not change, I noticed that sodium ions here are in ionic form and dissolved on both sides. So it was a spectator. Same thing also with my chlorides. They were spectators, and so all that really changed here was hydrogen and hydroxide forming molecular water. So my reaction, when I take a look at it, is H plus, OH minus, to give me H2O. Okay? One of the reasons why I wrote hydronium as H plus and why we have the shortcut in chemistry is in our introductory chemistry courses, unless we're really taking a close look at some intense acid-base work, all right, we just know that it's H plus, and it keeps our balancing easier for the end. All right, so just a little point of order here. We can just write hydronium as H plus in these problems. All right, one last little thing here. I'm just going to talk about it briefly. Remember that we said all of these reactions, including these net ionics, are quantitative reactions. And so most reactions will have something that is consumed first. What we say is this limits the reaction. Not only that, it limits the amount of product that are going to be produced. So limiting reagent limits the amount of stuff that you can get out of the reaction. It also limits the amount of other reactants consumed. If we have a little bit of extra of the other reactant, it is known as the excess reagent, but usually in a reaction, what we will see is that as we get into the stoichiometry in the next chapter, one of the things runs out, the other one remains in some sort of surplus or excess. All right, so chapter 7.1 kind of brings up this idea in theory, but when we have to start doing it in 7.2, 7.3, and 7.4, we will talk about it uniquely again for every one of those points. So look at 276 to 285, try the practice questions, make sure that you can do the non-ionic, all right, the single and double replacement reactions that we're looking at here. The total ionic, you can split apart what is supposed to be split apart, that you can find spectator ions, cancel those out, and write the net equation. That's the big takeaway and what you'll see being tested on 7.1, and there's a bunch of questions on it here. Good luck, guys. Good luck with that when we hit the stoichiometry hard in 7.2. So make sure you remember things like molar mass, have your data sheet, and yeah, there's going to be a lot of work to do here. Okay, so we're going to do our best with it. Good luck with 7.1. We'll see you guys when you're ready for 7.2.